The automotive industry is known to be one of the most competitive markets on the planet. Every inch a company can gain over their competitor, the better. One of these key areas where companies can get a leg up on their competitor is in automotive aerodynamics. By optimizing a vehicle shape to tame the environment through which it moves, drag force can be reduced, and as a result, fuel efficiency will increase. Fuel economy is considered a primary selling point in the automotive world, and for good reason. By increasing fuel efficiency, more customers are likely to buy your product. The tool of choice for optimizing automotive bodywork aerodynamics is computational fluid dynamics, or CFD, a well-understood, very mature field of numerical computation and engineering. It is based on solving differential fluid flow equations, such as the unruly Navier-Stokes equations, around and within the body being studied. Essentially, the fluid space is broken up into tiny chunks, hundreds of thousands or even millions of them, called cells, which make up a larger mesh. The fluid equations are solved in each cell to understand the fluid physics at every cell location in the fluid. The shape, size, and type of cells used in the mesh go on to influence the accuracy and the runtime of the result. As such, great effort goes into making sure the car geometry is CFD clean. It takes upwards of 10 days to go from a native CAD model to a CFD cleaned model. From there, the setup and the meshing process itself can take just as much time. All of this before getting into the simulation, which can take the same time again unless dedicated servers are used. Overall, you're looking at over 2 weeks of work just for the first iteration of potentially hundreds or thousands. But what if, after receiving the first iteration of CAD at 9 AM, you could have accurate, cheap, fully transient results by lunch on your laptop? SimScale is ready to take hold in the automotive aerodynamics market with unseen-before turnaround times, utilizing Pacefish, a GPU-accelerated lattice-Boltzmann method solver, and Amazon Web Services for high-performance, massively parallel computing. My name is Colm. I'm an application engineer at SimScale, and today I want to talk to you about 3 things. Number 1, the idea, to reduce automotive workflows from weeks to hours. Number 2, the implementation, to weave the SimScale platform with an efficient new solver and the powers of high-performance computing on the cloud. And number 3, the impact, unseen before turnaround times and an enhanced, cost-efficient, iterative design process. So first, the idea. SimScale is a web-based cloud computing simulation company based out of Munich in Germany. The platform offers a wide range of FEA, CFD, and thermal simulation capabilities from a browser tab, without need for any local hard drive space or installations. We have, for the last few years, been offering customers an easy method of obtaining easy, accurate results by taking advantage of high-performance computing with our partner, Amazon Web Services. We partnered with Pacefish, a CFD solver based on a modern particle density-based approach called the lattice-Boltzmann method. It is more robust towards user input and massively scalable, and developed by our partners at Numeric Systems. While building out our initial wind loading solutions in the architectural, engineering, and construction space with Pacefish, we noticed the tedious workflows and long turnaround times of the automotive aerodynamics world. We knew with HPC and this new solver at our disposal, we could tackle this problem. Drive AER is the standard validation case for the automotive world. Comprising of multiple models from the Technical University of Munich, it is notoriously difficult to obtain accurate results for all 3 models, the fastback, notchback, and estateback, all referring to different configurations of the rear bodywork. The idea is to do this validation project, all 3 models simultaneously in unseen-before turnaround times. Sounds easy, right? This case and the magic behind it in the back end will be the key to part 2, the implementation. It takes 3 things operating in unison to achieve such a task: an intuitive, easy, and robust platform, followed by a powerful, fast, and accurate solver, and finally, a lot of computing power. These 3 things, respectively, are SimScale, Pacefish, and Amazon Web Services. SimScale, The glue which binds Pacefish to AWS to the customer allows for setup of automotive aerodynamics simulations in under 10 minutes. Being web-based, the solution is independent of local hardware. Everything from this point on can be done off a laptop and a simple internet connection from your bed. Once the Drive AER geometries are uploaded onto the platform, the rest was all done in a web browser. Then after a brief 10-minute setup, including setting up the dimensions of the flow volume bounding box and inlet boundary conditions, the computational problem, defined by these setup parameters, was ready to be solved by the Lattice-Boltzmann method, a mesoscopic solver, as opposed to more traditional macroscopic solvers. From here, Pacefish's robust CAD-tolerant meshing algorithm takes in the geometry and forms the numerical domain, refining its accuracy down near the area of interest. The three dimensions of space, forwards, upwards, and sideways, are discretized by the lattice. Next, velocity and time within the lattice are discretized by choosing a lattice model. For Pacefish, this model is the D3Q19 model, allowing for 18 particle trajectories plus one rest condition. We now have a problem which is discretized in 7 dimensions. The solution is set running and particle velocity probability distribution functions based on the Maxwell-Boltzmann equation are modeled at 19 places in each lattice cell. These distribution functions go through iterations of collision and streaming steps which propagate the solution through time. This is the Lattice-Boltzmann method, a modern solution for complex transient flows. This is what is brought to the table by SimScale's partner, Numeric Systems, with Pacefish. As the solution marches through time, the distribution function value only depends on the cell next door. This creates an interesting opportunity in that the computational domain can be broken into many smaller chunks without many negative consequences. Assigning each chunk to a different computational core allows for massively parallelized computing. As you know, where central processing units, CPUs, typically have 4, 8, or 16 cores, graphics processing units, GPUs, have thousands of smaller cores optimized for numerical tasks. Drive AER was set up with a lattice size of around 160 million cells, a massive simulation size for old FVM-based solvers. Due to the Lattice-Boltzmann method's nature and ability to be solved in a parallel manner, this size of simulation is easy. Pacefish, an LBM solver written especially for GPU acceleration, connects with AWS GPU instances through the SimScale platform. The Drive AER case of 160 million cells was sent to the cloud, where 8 NVIDIA V100s, each with 5,120 CUDA cores, worked in parallel to push out results in record time. SimScale's load is very spiky as a result of the timing and distribution of when users submit jobs, and user jobs being different in their computational requirements. AWS is the only economically feasible way to run these workloads, especially considering the hardware cost of large GPU instances. AWS was the first to offer these state-of-the-art NVIDIA V100 GPUs for use in the cloud via their EC2 P3 instances. Our use of these instances has allowed us to push forward with this process, achieving accurate results much faster than before. New instances utilizing A100 GPUs are expected to set new benchmarking records and extend beyond the capability of parallelized CFD into aspects of AI. More information about the A100 GPUs on AWS can be found in the link provided. The 3 Drive AER models, with 160, 162, and 72 million cells, respectively, were sent to the GPUs stored in the cloud, all to be solved simultaneously. The transient data, force calculation, and statistical averaging of results to achieve a steady-state equivalent result was all done in the cloud. By lunchtime, the results were in. Comparing against the original Drive AER experimental results published by Angelina Heft at the Technical University of Munich, reveals greater than 95% accuracy on drag coefficient for all models. For the largest, most complex model of over 162 million cells, the simulation time was under 8 hours for fully transient result, a snapshot of which can be seen on the left-hand side. This indicates an unseen-before turnaround time in the world of automotive aerodynamics, and could only be achieved by utilizing new workflows assisted by high-performance computing. The fastback model had a deviation of 2.55% from experimental results, whereas the notchback model had a deviation of 2.24%. If multiple experimental sources are considered, for the estateback model, there was only a 1.6% deviation from experimental data. The trend between all models was also accurately captured by the solution. The solution, as mentioned before, was performed on an array of NVIDIA V100 GPUs, which retail for around $10,000 each. These GPUs are offered on instances provided by AWS, who always have the latest and high-performance hardware at a competitive price point. When taking into account the total cost of ownership of local servers, with power, maintenance, and depreciation of hardware, AWS offers a truly competitive alternative with their instance suite. To make sure we use those instances efficiently, Pacefish allows us to run a short initial phase of simulations on a CPU cluster to determine the resource requirements for the final run. That allows us to pick the ideal GPU instance for the job. The cost savings of AWS instances combined with Pacefish's over-provisioning checks allow for unprecedented cost efficiency of the solution. To further inspect the validation results, the pressure coefficient distribution across the top and bottom surfaces of the vehicle are investigated for all three cases. The fastback model is a configuration that many car enthusiasts will recognize. With a low-angle sloping rear, it is the optimal rear design for airflow, minimizing drag. Many modern automotive manufacturers have adopted the design philosophy behind the fastback to decrease drag and increase fuel efficiency. The simulation of this model was ran with 162 million lattice cells. Pacefish implements a novel method of accurately modeling boundary layer flows for under-resolved meshes, allowing us to achieve a surface cell size of 3 millimeters. This led to a solved result in under 9 hours. The key to the fastback model is the separation region and the pressure on the rear windshield. From the distribution graph on the right, it's easy to see an accurate correlation between the simulation and experimental results. The flow under the car is also accurately captured, with pressure coefficients correlating nicely with the measured experimental data. To further understand the flow, the separation regions can be identified on the platform as regions with reversed airflow. This is one of the several tools which can be used to understand flow patterns, all been built into the web browser platform. The pressure coefficient, mapped across the front windshield, shows the variation in flow, from stagnation at the bonnet to acceleration at the A-pillars. The visual data shown is a comparison between the simulated results and the experimental results. The experimental results, measured at several discrete probe points, are shown with a linear interpolation. Taking this into account, the simulation results almost perfectly match the measured experimental values. The notchback model is the precursor to the fastback model, the standard sedan car. It is a very familiar rear end shape with a sharper downturn and space for a boot. Typically, this model performs slightly worse in regards to drag than the fastback variant. The lattice size was similar to the previous run, with 162 million cells. 3 mm surface cells were again used to accurately model the boundary layer effects. The solution was achieved in under 9 hours. We can once again see the correlation in pressure coefficient along the center of the car on both the top and bottom sides of the model. Across the rear of the vehicle, the simulation matches the experimental data in regions, but deviates near the rear windshield and boot interface. We can take a look at the comparison between the pressure coefficient experimental values and the simulation results across the rear of the vehicle to understand this. The solver predicts slightly higher pressures in the very middle of the windshield, compared to the measured data, but this eases away to be closer to the experiment, away from the center line. The amount of probes measured here is also significantly lower than on the front of the fastback, so the inaccuracy of interpolating experimental results also plays a significant role in comparison. The estate-back model has different design philosophies than the previous two models. It is characterized by a high rear with a hatchback boot. This makes it perform significantly worse in terms of drag, but increases the size of the interior and has a positive effect on yaw behavior. This model was run with a smaller lattice size, as the solution was determined to be drag coefficient independent at a lattice size of 71 million cells. As a result, the solution, although only running on half the amount of GPUs, was finished in under 4 hours. As before, the pressure coefficient distribution can be seen for this final model on the right-hand side. There is a slight discrepancy between the measured values on the rear windshield and the simulation values, which many solvers have encountered in the past. As the solution is fully transient, interesting time-dependent behavior can also be seen in the model. As a result of the abrupt end in the roof, this could be an explanation for the small discrepancy in the results on the rear. Rapid oscillations in pressure, which is shown in the bottom image, can be seen flowing off the back of the model, a behavior which could only be seen with a transient solver. The vortex structures, which are shown in the middle image by a vorticity plot, are also very large in this region. This influences both the pressure and the velocity, which is also shown at the top. The full result set and project is available on the SimScale platform by using the QR code here, or navigating to it on the SimScale website. With the drive AER validation, a new player enters the automotive aerodynamics playing field. A hidden advantage of the lattice-Boltzmann method is that it requires a Cartesian mesh, which is a robust and simple way of creating a mesh compared to other methods, allowing us to take geometries which typically would not be suitable for CFD and handle them reliably without a problem. We can compare a typical automotive aerodynamics workflow with the workflow proposed by SimScale. Current automotive workflows consist of taking the final assembly and spending 10+ days forming a script that can create a cleaned model to be used in CFD. SimScale bypasses this completely, allowing for the final assembly to be imported straight into the platform. No need for those 10 days of cleanup. Current automotive workflows then take several days to mesh, ensuring cells are within mesh quality metrics and resolved to a specific level in specific regions, and can take many man-hours in multiple days. SimScale renders this unnecessary, as LBM lattices require cell aspect ratios of 1. The pacefish meshing algorithm is robust and tuned for automotive applications, resolving detail where it needs to be resolved. Fully automatic meshing settings were used for all drive AER models. Current automotive workflows then require a dedicated local server to get results out in a reasonable amount of time. If this is not available, then simulations can take days or even upwards of a week. SimScale, taking advantage of the massive parallelization capabilities of the lattice-Boltzmann method and the high-performance computing capabilities offered by AWS, can bring simulation time down to hours. In a market where iterative design is key and simulation runs can number in the thousands, reducing simulation turnaround time by over a factor of 10 can change the landscape. Weaving the lattice-Boltzmann method with AWS high-performance computing onto a web platform, SimScale offers an automotive aerodynamics solution to transform fortnightly turnaround times into nightly turnaround times. Thank you for your time.